the discovery of acid-base theory. Okay, so scientific theories develop over many years and they are improved upon by different sciences. That's just how science works. Science evolves constantly. Even the science today is constantly being adapted or tweaked or improved or sharpened or applied to everyday life, because that's the whole point of science, is it explains things around us and allows us to develop new technologies and theories. So what we're doing here is we're looking back. We're going down the timeline and trying to look at how our current way of thinking has been adjusted and adapted over time. So this is the history part of it. So what we're going to look at is the link between oxygen and acids. And this person, a Frenchman called Antoine Lavoisier, Lavoisier was famous for the study of oxygen and discovered that oxygen was responsible for the combustion, such as burning fuels, for example, and named the gas in 1778. And Lavoisier also knew at the time, he was aware of formulas of acids such as sulfuric acid was H2SO4 and nitric acid was HNO3. So it was way back in 1778, so he knew that already. He suggested that all acids must have oxygen in. That was his theory. That's what he came up with. But he didn't know the formula of other acids such as hydrochloric acid. So you could kind of excuse him for coming up with that theory, because the acids that he was aware of, they all contain oxygen. So he made that link between the two, and of course he found oxygen, so he had some kind of bias towards that as well, but he wasn't aware of other acids. So the proton and hydroxide ion theory, this was a little bit later on, 1884, and you may have seen, especially in the previous topics, which is Arrhenius equation. So this would have been in the rates of reaction section, which is the how fast section of this of module 5. But Svante Arrhenius was Swedish, and he came up with a theory to do with physical chemistry. So he's a physical chemist, that's what he was. And so he came up with proton and hydroxide ion theory for this. And Arrhenius said that acids donate protons, that's H plus ions, and bases release hydroxide ions, which is OH minus ions. So that was his thinking. And he also suggested that when an acid and a base react, they form salt and water. So, okay, so he's a little bit closer to what we understand it to be currently at the moment. But he didn't explain why chemicals like ammonia are bases. And we know that ammonia is a base. But the problem is, he said that bases release hydroxide ions, but ammonia doesn't have hydroxide ions. So his theory is much closer to where we are now. So it took these two people, he needed two heads to do this, which was Bronsted and Lowry, who were Danish and British chemists. And basically they collaborated and improved the theory that Arrhenius did in 1923. So that's much, much closer to home, just under 100 years ago. So there's the picture. So Thomas Lowry was British scientist, and Johannes Bronsted was Danish, and they came up with an idea that acids are proton donors. And they also said that when we mix acids with water, that hydrogen ions, that H plus ions, are actually released into solution. Now, H plus ions, they also said they don't exist on their own in water. They actually form hydroxonium ions, which is H3O plus. Sometimes you might see them as hydronium ions. And basically, it's these ions that make something acidic. But for simplicity purposes, what you will see much more common is just the use of H plus. It's a lot easier to write H plus rather than H3O plus. But just be aware that what makes something acidic is not just H plus ions, it's actually H3O plus. So here's an example. So HA represents an acid, and you'll see that used quite a lot in this video. Reacting with water, and it forms H3O plus, that's your hydroxonium ion or hydronium ion, and that produces A minus. So this is the generic equation. So Bronsted-Lowry bases are proton acceptors. So that's what he said. So he said that acids are proton donors. So they said, should I say? They said that acids are proton donors and bases are proton acceptors. So when we mix bases with water, they react with the H plus ions to form hydroxide ions. That's OH minus ions. So an example is when you react a base with water, as you can see here, that produces BH plus and OH minus, and that solved the problem with the ammonia, because ammonia doesn't have OH minus ions, but it's actually the ammonia reacts with water to form the OH minus ions, and indeed so do other bases as well. So this really kind of answered some of the issues of some of the anomalous chemicals that didn't fit them theories. So this is, as you may have seen already, this is the theory that we predominantly base chemistry around now, until another scientist comes along and explains other issues. Then this is the theory that we use. So they call it the Bronsted-Lowry theory. Okay, so let's, on the topic of acids, so let's look at different types of acids. So polyprotic acids is an example of acids that you will see in everyday chemistry. So some acids donate more than one proton, so it's not just exclusively one proton. Some have two, and we call them polyprotic or even polybasic if they accept protons. So, for example, HNO3 is a monoprotic or monobasic substance. So, for example, 1 mole of HNO3 will produce 1 mole of H plus ions. So here's another one, which is sulfuric acid. So sulfuric acid is diprotic. 1 mole of sulfuric acid, H2SO4, will produce 2 moles of H plus ions, because it's got 2 protons for every molecule of sulfuric acid. Phosphoric is triprotic. So it has 1 mole of phosphoric acid will produce 3 moles of H plus ions. So you've got to be able to be familiar with these acids. These are acids, these are strong acids, but these are acids that you see quite regularly in chemistry. So you'll be familiar with them already, but you do need to know the formulas for them. Okay, so acids and bases. Acids react with bases to form salt, which are pH neutral. So we call these neutralization reactions. So H plus ions that are produced from acids, they react with the OH minus ions that are produced from alkalis, such as sodium hydroxide. And these make neutral substances, such as water is a classic example. So a simplified ionic equation is H plus reacting with OH minus to form H2O, and this is a reversible reaction. So let's look at a specific one. So this is hydrochloric acid reacting with lithium hydroxide. So this is your base and this is your acid. This forms lithium chloride, which is the salt, and water, which is the neutral byproduct that's produced from this. Now salts are made from the metal, from the base, or if it's the ammonium ion, if it's an ammonium substance, ammonia, for example, you're reacting it with, and it's made from the non-metal other than hydrogen from the acid. So you can see here that we have our non-metal, which is chlorine from HCl, and a metal from the base, and that forms lithium chloride, which is the salt. Here's another example. So this is nitric acid reacting with potassium hydroxide, and that forms potassium nitrate and water. Again, so we're taking the non-metal part from the acid, and we're taking the metal part from the salt to form from the base to form the salt. We've got to be careful with ammonia, because ammonia doesn't have an OH in there, so it doesn't produce the OH minus ions, so it uses water to produce the OH minus ions on its behalf. So it does that by accepting a proton. So you've got NH3 here, accepts a proton from water, and it forms ammonium ions, which is NH4 plus, and OH minus ions. So this, remember, anything like this in solution is what makes it basic. So if we can, even if it's directly or indirectly, if we can produce OH minus ions, then we produce a basic solution or alkali. So an example, it'd be ammonia reacting with acids to make ammonium salts, but no water. So unlike these ones here where they produce water, when we react ammonia with an acid, we don't produce water, we just produce a salt, which is neutral as well, so that's fine. So this is ammonia reacting with sulfuric acid, producing ammonium sulfate, which is the name of the salt there.